Hi, I'm Igor. I'm a data science living in London, and in this video I'll explain to you what the exponential distribution is. This distribution appears a lot in machine learning, particularly for survival models and also churn prediction, so it's something definitely well worth knowing if you're a data scientist. The things we'll cover in this video are: what is the exponential distribution, what are its origins, deriving of first principles, and how we can use it in Python. So let's get into it. So let's first begin with understanding what is the exponential distribution. So in a nutshell, the exponential distribution infers a probability of the waiting time between events. So it's just saying how long is until an event happens given it happens at a certain rate. A basic example would be for the waiting time until someone makes a claim. And you can see why it's very useful for insurance companies, because if they can know how long it takes for a customer to make a claim, they know how much premium they're making, so therefore they can better price a policy. Now, something that's very useful to insurance. In fact, that's the whole business, predicting how much a customer is going to cost them. And so the exponential distribution plays a critical factor in this big multi-conglomerate industry in the world. So to really understand the idea of waiting times, where this comes from, we need to start understanding the Poisson process. So the Poisson process is linked to the Poisson distribution, which is a video I discussed in my previous video that you can check out. A link somewhere on the screen here. And the Poisson process is used to describe a counting process where the events happen at random but at a given rate. So going back to our claims example, we may know that we get, say, 5 claims per hour, but we don't know when those 5 claims are going to happen. So those 5 claims may happen right at the beginning, right at the end, or spread out evenly. The point is, we know the rate, but not when they happen, and that's something known as the Poisson process. Now, the Poisson process, kind of what I hinted at recently, or just now, is linked to the Poisson distribution. Again, I've done a previous video on this, but the Poisson distribution is essentially a distribution that measures, given something occurs at a mean rate, what is the probability of some value occurring with it compared to that mean rate. So we'll go through an example in a second, but what the Poisson distribution looks like is this. So this is the Poisson PMF. So all it is, we have lambda, which is the expected number of events happening, and we have x, which is what we want to work out of what's the probability of these number of events occurring. Here E is Euler's number as normal, and x is the random variable, which is a Poissonly distributed random variable. Here's a video, again I'll link it somewhere on the screen here, that describes the Poisson distribution in a lot more detail, so feel free to check that out if you're unfamiliar with Poisson or you want to get a bit more understanding than we're just going into in this video. So let's go through an example of the Poisson distribution. So Poisson distribution is, like I said, it basically tells you if something happens at a mean rate, what's the probability if we get this many counts, given we have this mean count rate. So going back to our claims analogy, we have a time period of 1 hour and we expect around 5 claims per that hour. So what is the probability of there only being 1 claim? Well, in this case, we would have 5 is our lambda, that's the average claim, that's what we get. Now these expected claims we get in an hour, and we work out the probability of only receiving 1 claim in an hour. So in this case, what we do, we just sub in the numbers. So 5 is our lambda, 1 is our x. We sub this all into this formula here, which will be shown in the previous video. This is the Poisson PMF, and we get roughly 3.3%, or 3.4% if you round up. And so it's very, very small. So it's saying that given we have a mean rate of 5, to only get 1 is very, very unlikely. And that's kind of what Poisson distribution is saying. It's just saying how likely is a certain number of events going to happen if we know it happens with a mean rate. Again, I've kind of reiterated that point many times, but that is the main gist of the Poisson distribution. And we can even plot the PMF as a whole spectrum over all the possible number of claims you can get. So in this case, we see here is a Python script. So what we've done is imported the Poisson function from SciPyStats. We've got numpy and matplotlib, which is our plotting function. We're then going to treat x, which is the number of claims that can happen. So what we're saying here is that we want to work out a probability, or what the distribution looks like when we have 1 claim, 2 claim, 3 claim, all the way to 15 claims. We're then going to pass this into the Poisson.pmf, and then we're just going to plot a result. Very simple. And this is what the result looks like. And as you can see, the most likely number of claims we're going to get in that hour period is 5, which makes sense because that is the mean rate, so therefore that's the most likely. And either side of that mean rate, we see here that we're very, very likely to get 0, a bit more likely to get 1, a bit more likely to get 2, and it slowly climbs up until 5. And then you see it tails off again as we get to more extreme values. So basically, the more we get away from the mean rate, the less likely that count is going to happen in that time period. Should be quite intuitive, makes sense to me. Again, check out the video if you're not following this too much, and you can get more of a deeper understanding behind the Poisson. Now the point is, why are we doing this? Why am I talking about the Poisson distribution when it's videos about the exponential distribution? Well, they are linked, because the exponential distribution is kind of like the inverse of Poisson, as the exponential distribution describes the waiting times between these events. So whereas the Poisson is kind of focused on how many events happen, the exponential distribution is saying, well, what is the duration between these events happening, or the probability of the next event happening in this time period. So they're kind of the inverse of each other, and they complement each other very nicely. So you can even derive the exponential from the Poisson. And how we do this is by starting with assuming that in a given time period we've had no events. So in this case, you see here, x equals 0. So what we're saying here is that given we've had some sort of time period t go past, we've had no rates, so no claims have happened, so that's 0. And what this means is that we get eta minus lambda. That's probability of getting nothing, zilch, in our rates, or in our time period. Now, obviously, this is just for one time period, and we can generalize this to be t time periods. And all we do then is therefore multiply it by t. We're just saying that we haven't got any for this time period, what's probability of getting for the next one and for the next one. And we're just saying we're going to wait until big T time periods to get the first event. So it's a bit of just an expression, mathematical sort of thing you can think about. Don't worry too much about it. It makes intuitive sense. Just go over your own time, and I'm sure you kind of grasp the concept. But all we're saying is we're going to wait a certain amount of time periods to our first event. What is the probability of this happening? It's just a mathematical expression. Don't think too much into it. So what we are saying is that we have to wait t time periods. In our claim analogy, this is t hours until the first event claim occurs. So going back to the claims analogy, we're going to wait t hours until our first claim occurs. That's all this expression means. Again, not too complicated. Once you really think about it, I'm sure you understand it. It's quite intuitive. Then, on the other hand, the probability that an event does occur within that time period is simply 1 minus this expression here, because it's probability sum to 1. And this expression is also known as a cumulative distribution function, CDF. And a common result in statistics is that the derivative of the CDF is the PDF, the probability density function. And so by deriving it, what we get is the exponential distribution. We get lambda eta minus lambda t. So there we go. We've derived the exponential distribution PDF from first principles from the Poisson distribution, and it was that easy. It took us like 4 or 5 equations. So it's really, really great. If you're kind of unsure about this process, rewind the video, go over it slowly. Again, like I said, it's not too complicated, but it does take some time to get your head around the steps we've done and to really grasp the whole process. Right, now we've derived the exponential distribution from scratch. Let's now show an example of it. So let's go back to our claims example that we've done the whole video. We have 5 claims per hour. This means that on average we have to wait 12 minutes for the next claim, right? Because we have 60 divided by 5. And what this looks like is this. So here all I've done is I generate a range of values of x. So in this case, x is hours. So saying 2 hours is kind of our range. So 0 to 2 hours, what's probability of waiting 2 hours until we get the next claim? In here, y is the PMF. So remember we had 5 np.xp, which is just the exponential function of minus 5 of x, right? This is just the formula we had here, right? All I've done is I've added it into this code and I've plotted the result. Now, as you notice here, remember the PDF is on the PMF. So the probability of 0 is not actually 5%, right? Or 500%, that'd be incorrect. To find the probability of something happening in the PDF, you have to integrate it because it's continuous, it's not a mass function. So, if you want to answer the question, what is the probability that the first claim occurs within the first hour? We don't look at basically 1 and infer it like this. What we have to do is we have to integrate from 0 to 1. So in this case, 0 to time 1 hour. And we see the result roughly if we integrate to the function, as we normally would. we get roughly 99.3%. So what we're saying is it's very, very likely that the claim will happen in the first hour, which makes sense because we expect it to happen on average every 12 minutes. So you see those kind of adds up. So eventually we should get the first claim within the first hour by, pure statistics or pure probability. But there is a small chance that we may not get it, 0.7%, that we may keep on going. But as you can see, the more you integrate this line, like if you go to 2 hours, the bigger this number will get. And obviously the integral under the whole PDF is 1. But you see here, what we're saying is the integral between like 0 and 0.5 is where the majority of the claim will happen. So again, the PDF, don't think of it as the PMF, like don't read off the graph. You have to integrate it to get the probabilities, which is kind of, you got to make sure what plot you're reading and what it really says on the y-axis. For the Poisson, we could read straight off it because it's a mass function. But for the exponential distributions of PDFs, we can't quite do that same process. But the way you do it is by integrating like we've done here. Now, I hope that makes sense. Again, go through in your own time if you got a bit stuck, but it's quite intuitive once you get the hang of it. So thanks for watching this video and also sitting through my talk on exponential distribution. I have this whole thing as a blog post, so if you want to read it and digest it in your own time, then I'll leave this blog post in the description below. And yeah, I highly recommend you check that out because it'll give you another way of visualizing the whole thing. These are my socials, obviously YouTube, GitHub, and X, or formerly Twitter. Feel free to check me out there. And also I write a newsletter about data science every Monday morning that'll go right into your inbox. That's also linked in the description below, so make sure to check that out. And if you enjoyed this video, make sure you like, comment, and subscribe, and I'll see you in the next one.